Greetings and welcome to my new calculus channel. My name is John Gabriel. So today I'm going to show you a neat little trick that you can use to see what any function looks like within the same range window. So any function, regardless of the type of function, can be reduced to having a range between pi over 2 and minus pi over 2. So how do we do that? Well, the trick is instead of plotting the y value as an ordinary number, we plot it as a slope. Okay, so that means rather than plotting x, we're actually plotting the inverse tan of x. Okay, so this is the inverse tan of x up here. Now, if we had 0, we'd have the x-axis, and if we had a very large number here, it doesn't matter how large, we'd get very close to pi over 2. It never gets to pi over 2, but it gets very close. Also, if we had a very small negative number, it gets close to minus pi over 2. All right, so now what about simple curves like x squared? So this blue function here shows you, blue curve shows you the ordinary x squared, but turns out that we can give it a range between 0 and pi over 2, okay? This is x squared. Similarly, if we had to do that, we can give it a range between 0 and minus pi over 2. They're two different functions, but you can see the entire function within this window. All right, so why is that useful? Well, if you had a more complicated function, such as this one here, let's go to this one over here. So you've got that. Let's put that inside there. I'm going to give you a few examples. Okay, so if you had that, this is really what you'd see in terms of the function itself. So, and if you moved this down, you could, for example, say minus 6, and it would be outside of that range. Okay, so a lot of stuff is happening here. You've got maxima and minima and inflection points, and you can see all of that very easily in this short window here. So you can tell a lot about the function by just reducing it to a representation through slope, which is angle measure rather than just the ordinary corresponding y value. So that's pretty useful. There's a lot of information and facts that I haven't shared about this, and at this stage not prepared to share, but I'm just giving you this example so that you can study functions more effectively. And if you had a more complicated function like this one here, let's look at this. This is the one for the normal distribution, and that's pretty much it. Now you'll notice that the normal distribution is very close to the actual arctan function. Okay, very close. So there's very little difference, and it's one of the only functions that are very close, and it has a range which is between 0 and the maximum point here, which is 1 over root 2 times pi. Okay, because if you put 0 in there, that becomes 1. So this is just the reciprocal of root 2 pi for the normal distribution function. Then another interesting function is this one here. And if you do that, now you'll notice that if you increase this value, let's say to 3, then you'll get something a lot closer to the actual value of the arctan function. And if you make it 5, almost the same, right? And you can make it so that it appears that there's no difference at all, right? So basically what that does is it just flattens the curve. And if you make it smaller like this, then it takes it out of, well, the slope function always remains within this range, but it will take this 1 over 1 plus x squared function that you normally had outside of the range. But this is what it looks like. So that's pretty much it. I just wanted to share that with you. There are some really fascinating aspects about this, which I have researched and studied, not prepared to share at this time. Perhaps when my contributions and comments are more positive and contributions increase to a level that I'm satisfied with, I'll share some more information. But for the time being, that's it. If you're not already a subscriber, become one. Tell your friends about it. Follow me on academia.edu. And until next time, I'm John Gabriel. Goodbye.